let's give you the nuts and bolts of partial derivative. And we already went up and talked about the idea, right? So let me see if I can draw my picture that I like to use for this.
I'm gonna draw it, you know.
What?
Yeah, come on, conserve.
That's why I just refill this.
All right, so here's some function of x and y, right? You guys all with this? I've got kind of a surface draped over whatever. So here's my f of x and y. And I want to give you the definition of what a partial derivative is, right? Okay, so fx of x and y, right? Which we're also going to write as the partial of f with respect to x of x and y. And sometimes we'll leave the of x and y off of that.
It's not a 2, it's like a
Yeah, it's like a soft
squiggly.
D.
Okay.
The reason it's a soft D is that it's not actually a derivative, right? It's just part of a derivative. And so instead of using the D that we used before, we're going to use this slightly softer D that's going to mean like, it's part of the D we used before. Cool? And it really is going to feel a lot like that, but this is going to remind us that this function depends on other stuff, right? The, this one? That's an R.
No, that's rho. It's like a figure eight.
It's like a, yeah.
Oh, a delta?
Yeah, that.
Yeah.
That's
No.
like a half.
This is like a melted.
No, this is a different symbol.
Oh, a rigid 2.
It's a different symbol. Don't care. It's called a partial. Okay?
Rigid 2?
So, the way you get a partial, right, is you take the limit.
What's so fun is videos when you script.
I have to delete the whole thing. No, I'm just kidding. We'll leave it. Whatever.
Just sub
So-
in Russian.
I want to take the limit h tending to 0. How would you take a derivative of f if it only depended on x? Like, what's your usual formula? Okay, so you do f of x plus h, right? Okay, but then there's also a y. And then what would you subtract? Okay, so we'd subtract f of x, but then there's also a y. And then we divide by h. Okay, so how's the partial with respect to x work? It works a lot like a regular derivative, except, and there's also y's,
Y
right?
constant.
Yeah, you treat y as a constant and just do this then. Okay? The other partial, the fy of x and y, which we would write as the, how did I say that thing last time?
Partial f.
Partial f with respect to y of x and y. And I think your book usually omits this of x and y, and I really will in the future. I'm just writing it now to kind of drive home that thing's a function of x and y, right? How do you get this one? Okay, take the limit h approaching 0 of
Why is it f of y plus hx?
Y plus h with an x.
Y plus eight.
x comma y plus h.
Yeah.
So why does that feel funny in this time? Well, in this one, the h I'm adding has to go in the second coordinate, right? Because that's where y is. And then I need to subtract f of x and y and divide by h. Okay. So let me draw a picture for you. I have this picture of my function, right? Okay, so here's some slice parallel to the, yeah, that's parallel to the x-axis, right? That's me being down here. There's my slice parallel to the x-axis. See that? Okay, then that's a one-dimensional function, right? That's only a function of, yeah, it's only a function of x, right? Because to get that, I set y equals some constant, right? Okay, so if I set y as some constant, then it makes sense to take a derivative along that, right? And so what's that thing going to tell you? That's going to tell you about the slopes of the tangent lines in this direction. You guys see that? The other one, right? So that blue one is my fx, right?
What constant is this?
I did this time. I don't in general. So then the other way, right? How am I going to get that?
Set that.
So I'm going to set x as constant. See, I did in that time.
Thought I was seeing this one, but I was
No, not at all. So that's going to give me fy, right? And that's going to tell me about the slopes in that direction, right? Front and back. Cool. So this is, right, if I go out and stand on a point x and y, right, and the x-axis is this way and the y-axis is that way, fx tells me about the slope to my side, and fy tells me about the slope front and back. You guys cool with that? Is that all the information? Doesn't really seem like it, right? It's only two directions, and there are infinitely many directions, right?
But if you
have
if you
components.
pair each of them up, you could get somewhere, right?
Kind of, yeah. We'll do that in the next section. So it turns out that this is kind of enough information.
A little bit of x.
Because we're approximating everything anyway, right? Like that's really what our tangent line does, is it approximates the function. So we can get away because we chase an approximately equals in the right way. It's cool with this? Check definitions. So procedurally, for fx, you take the formula, differentiate, treating what? Yeah, y should be a constant, x should be a variable. To do the other one, fy, you're going to treat x as a constant, treat y as a variable. That's going to be the hard one. Right, because you're used to treating y as a constant and fiddling with x. Treating x as a constant is going to take a little getting used to, but it's all there. Cool?